Okay, well, John has nicely covered the scientific accomplishments of the telescope. I'm an engineer. I'm going to talk to you about the technical aspects of the telescope. I'll go through things like the construction, what it cost, to compare it with some of the contemporary telescopes. I'll go through its first light, the optics of the system, some of the early instrumentation. I won't have time to talk about things like polarizers for Jacques Vallée or station computers for Lloyd Higgs, but I will get into the resurfacing project, the cancellation and its mothballing, its later revival. And just to add, the name of this talk is A Brief History. It's a brief history because I have 400 slides and you're seeing only 80 of them. Okay, so here's a nice picture of it in the early days, 1966. It went into operation in May 1966. It was the largest telescope ever built in Canada. It was one of the first large telescopes designed to operate at wavelengths as short as 3 centimeters, 10 gigahertz. It was the largest fully steerable telescope in North America dedicated to radio astronomy until the 100-meter GBT telescope was built in 2000. Had the plans for resurfacing gone ahead, it would have been one of the largest capable of observing at 115 gigahertz and maybe even 230 gigahertz. Last, when it was canceled in 1986, it was one of the first major national facilities ever to be faced with being put into mothballs. So what's my connection? Well, I was a summer student there in 1977, and this is one of the widgets that I built for the 150-foot telescope. I then went on to grad school at Queen's. Mike Kestevan was my advisor, and we looked at the recombination lines coming from the direction of the galactic center. For some reason, they hired me as a digital engineer in 1979, so I designed a whole bunch of microcomputer-based monitor and control modules. I was the lead engineer on the autocorrelation spectrometer. Had the resurfacing gone ahead, I would have been in charge of the IF and the back-end systems. And after the resurfacing was canceled and half of the astronomy section was laid off, I was the most senior engineer left in the receiver group. And so it fell to me to make numerous trips to ARO to scavenge and take inventory of the surplus equipment. And it's by far the most depressing job I've ever done in my life. So here's a picture of what it looks like, 1971. If you go to Google Earth and you try to look at it, it's very fuzzy. So this aerial image from 1971 shows some of the more whoops, what's that do? It's the top is the laser, there we go. So there's the Lake Travers, here's the Petawawa River. You can see down here where the CN station comes by. There's where the staff house was. Site 1, where the solar patrol is over here. Further to the west is Site 2, with the horn and the 10-meter. The 46-meter was at Site 3. Site 4 was the U of T 60-foot dish, and then the solar interferometer was at Site 5. So a little bit of who's who during the ARO era. It was originally built and operated by the Radio and Electrical Engineering Division, and until 1975 when it was transferred to the newly formed Hertzberg Institute. So here are the head of the divisions. Back early, Ballard, followed by McKinley, followed by Cumming. And when HIA was formed, it was Jack Locke for 10 years, followed by Don Morton. The head of the radio astronomy section, and the section had many names through its life. It was first known as the microwave section, then the radio astronomy section, then the astrophysics branch, and then when HIA formed, it became the astronomy section. But we had sort of Jeff Meller, Jack Locke, Nom Broughton, and John McLeod was the head of the section at the end. The head of the receiver group in the Reed era, it was Bill McLeish, Bill Blower during the HIA era. And superintendent, the chief operating officer up there, was a number of them, but the two at the bottom, Bob Dustin and Ross Austin, are the ones that probably people will know most. And if you look at this list of names, you can see several things. That if your name ends in Ustin, you have a good chance of being the superintendent. If your first name is Bill, you have a good chance of being the head of the receiver group. If you're Jack or John, well, you might be a section head. Okay, so here's one of the drawings for the proposal, and this is from 1961. It kind of sort of almost ended up looking like that. It is neat in that it shows the drawing of the cherry picker, which would become an indispensable piece of support equipment. The only way to get up to the focus cabin easily was with that 100-foot cherry picker, which made it one of the tallest in North America. By '62, they had some nice models that were fully steerable. You had little sort of buttons that you could move it up and down in elevation around an azimuth, so it was fun to play with. So here's a plot of the effective area of the contemporary paraboloids of 1965. So there's the 3 centimeter line where we want it to reach. Here's the NRAO telescope, so it's this dashed line that runs through there. So here's Jodrell Bank, nowhere near 3 centimeters. Parkes is rolling off. Haystack has got fairly good area, but it starts off small at 120 feet. And so the competition was the 140 foot at Greenbank. So here's a picture of one of the original contract drawings, and it's kind of hard to see, but you can make out things like the inner 120 feet were covered with solid panels, 216 of them. The outer 30 feet was covered in mesh panels, 216 of those. The backup structure consisted of 36 ribs. 4 feed legs held up the aerial cabin at the apex. There's a large metal structure here where the vertex hub and the counterweights were. There's, of course, the base tower, and then there's a canopy which covers the azimuth track so that snow doesn't accumulate on the rollers and things like that. There's a better picture here that comes from an article by Mike Jeffrey, who was one of the project engineers for Freeman Fox and Partners. There's a large number of items that he points out, but I'm going to concentrate on this thing right here, which is the master equatorial unit. In those days, when you didn't have big, expensive computers, the best way to steer a telescope is to put a little optical telescope right at the center of the axis. It sits on an isolated pillar here, so it's decoupled from what's happening to the big telescope. There's a fun little spiral staircase that was always fun to climb around. And so what you do is you point the optical telescope to whatever RA and Dicke you want it, and there's the isolated bearing. And then there's this thing right here, which is the error detector. So it's on the radio part of the telescope, and so the error detector finds where the optical telescope is looking at, and then drives the radio part of the telescope to line up where the optical section was. So that's what the master equatorial did. So here's an article in the press from 30th October 1960, and it says the proposed telescope, costing in excess of $500,000, is similar to the design of the one put into operation by the Dominion Observatory near Penticton. However, it will not duplicate the work of Penticton. ARO never did actually work at L-band, and it certainly didn't work at TIM's Z-min frequencies. It also says all power required for operation is supplied by diesel generators, and that was the case for the first couple of years. It was powered by diesels. Now, in October of 1960, we have the NRC telescope tender bid decision soon, and it says down here, construction of the NRC $2 million Lake Traverse Radio Observatory has been approved. Planned for completion in 1964 despite the government's current austerity program. So the more things change, the more they stay the same. So the first thing built was the tower. You can see them here. The control building was already built, and if you looked out from inside the control building, you can see they're hard at work. This is late 1962. There's the diesel generator. Now, the prime contractor was Dominion Bridge, based in Montreal. And so here they are in January of '64, welding up the parts of the hub, which consists for the vertex system. And there are lots of metal here. And there's the 2 sections that will make up the upper and lower hub section. So now those have to be carted off to Algonquin Park by train. So by April '64, that part was complete. In early '64, the tower was certainly complete, and in October they are raising up the top section of the hub. So now it's ready to have the backup structure put on in October of '64. So here they are in February 65, raising the first pair of ribs from the ground. Each of these pair of ribs weighed 6 tons. Here they are with 3 pairs of ribs up. In February, it was half complete. And by June of 65, all of the ribs are up in rings, and they're starting to put the panels on. The panels were also built at the Dominion Bridge. They were rolled. They were 1/4-inch steel plate, which was rolled to give you the correct compound shape that a paraboloid requires. There were lots of holes that had to be drilled into each panel so that you could fasten them. The Algonquin dish, unlike many dishes, the panels were an integral part of the backup, the structure support. So the ribs were there to hold the telescope together, unlike a lot of telescopes where the ribs just sort of float on top of a backup structure. Each point of each panel had to be measured at about 1 point per square feet to make sure that it had the right shape for the paraboloid. And so here they are in June installing more of the panels. There were something like 15,000 plating bolts that had to be tightened. That's a lot of bolts. So in June, all of the solid panels are up. Now it's time to put the Tetrapod and the aerial cabin on. So here are pictures of the Tetrapod at Dominion Bridge. There's the aerial cabin. Now, because the aerial cabin had to be able to focus your receiver in and out, as well as the Gregorian subreflector in and out, there were 2 positioning platforms inside the aerial cabin. And you can never go into that aerial cabin without getting covered with grease. Here they are raising the 3rd leg. Whoops. There's the 3rd leg here. The 1st leg and 2nd leg are already up, and so now the 3rd leg is being put into place. So this is in July of 65. The master equatorial unit was built by Grub Parsons in the UK. So you can see the master equatorial unit sitting here, and in the background is the COCO. That's the coordinate converter, which is essentially an electromechanical computer. You would feed into it the analog signals that indicate what the RA deck position is of the master equatorial. You feed it into this thing, it would generate the azimuth and altitude voltages that you would use to drive the big dish over to where the master equatorial was sitting. You get it within plus or minus 1 degree. Then it would lock up through the error detector, and then it would start tracking the master equatorial. So it was a neat way of doing things, and all of the Deep Space Network telescopes did it like this, the big 64 meters. NOBIEMA used a master equatorial, as well as Parkes, of course.
It started at Parkes, right?
Yes. Yep. Burns Wallace was the guy who came up with the idea. Yeah.
And was it the same British firm that did the Parkes?
No, a German firm did the one in Parkes. So here they are raising it up in the mid of winter, 1965. And here it is sitting on top of that isolated pillar that I mentioned, and then that'll be covered over to protect it from the cruel Canadian winter. So here's Jack Lock's picture again. Everybody loves this picture. So 1966, it's completed. So here's the contract between NRC, the purchaser, the Freeman Pox and Partners, the consulting engineers, and Dominion Bridge, the prime contractor, from December 1963, and it was 106 pages long. The key page is the summary of how much it cost. It was $3.5 million in 1963, which today would be $27 million. More interestingly, you can go through and look at what each item cost. All the tubular ribs and ring girders in the backup structure was $180,000. The tetrapods were $16,000. The apex cabin was $9,000. The solid panels were $221,000. The mesh panels were $111,000, and it took over $9,000 just to paint it. In the turret and the hub cost about $100,000. The counterweights was over $100,000. The spiral staircase was $9,000. And painting of the canopy and the vertex and everything was $32,000. The control desk, $20,000. The analog computer for the servo system was $162,000. The master equatorial, $177,000. The error detector was sort of $80,000. The COCO was $53,000. And the racks and encoders for the altitude and azimuth on the dish was $20,000 each. So let's do a little comparison to the 150-foot with contemporary telescopes. So there's the Parkes 210-foot, the big sister from the colony down under. And then the other one we'll look at is the 140-foot at Green Bank, sort of our rich American cousin. So when you look at pictures of Algonquin or Parkes, you sometimes say, now hold it, which telescope is that? Because there's this tree-lined access road, and you really have to think what it is you're looking at. Well, first of all, ARO was built in the middle of a wilderness of coniferous forests, and half the time it looked like this. But of course, Parkes, half the time looked like that, and there's Osti Helm and the sheep. But instead of sheep in the paddocks, it's now all golden canola. A fellow by the name of Colin Blackwell, he was one of the design engineers, and he had an interesting article where he sort of compares the two telescopes side by side. And there are a few interesting things that you get out of this. Obviously, the Parkes dish is 40% bigger in diameter, but oddly enough, the Algonquin telescope is 7¼ feet taller. And that would surprise me, because every time I see the base tower of Parkes, it looks way bigger than the ARO. But the elevation axis in Algonquin is actually 7 feet higher than the Parkes dish. Parkes could only reach to within 30 degrees of the horizon. Algonquin could get within 10 degrees, which meant we could look at the galactic center for 4 hours, from before it set. Parkes, the amount of superstructure and counterweight, essentially the weight above the azimuth track at Parkes was 1,000 tons. Algonquin was 900 tons. Considering it was a smaller telescope, there's obviously much more metal in it. So here's the Algonquin dish. There's 36 cantilever truss ribs, 75 feet in diameter. Parkes was 105 feet, and there were only 30 truss ribs, but the designs look very similar. Surface accuracy for Parkes was plus or minus 1/5 of an inch. Algonquin was plus or minus 1/16 of an inch. Note that both telescopes have exactly the same size hub, which is also surprising. Now, cost-wise, Parkes was $1.3 million in 1959, and that included the base tower. Algonquin was $3.5 million in 1963, but the base tower was under a separate contract. Talk about Green Bank. I won't go into the tale of woe about the fact that it started in 1958 and it wasn't completed until 1965 because of these brittle fracture cracks. But it was only 4.5 dB over budget. In other words, it cost $13 million. It remains the largest equatorial telescope ever built. Let's back up here. So when the initial RMS from the best fit paraboloid for Green Bank was 36 thousandths of an inch. Algonquin was 41 thousandths of an inch. That gave Green Bank an efficiency at 2 centimeter wavelength of 43%, and ARO operated a slightly longer wavelength, and it had 42%. So they're kind of sort of similar. After holography was invented, in 1986, Green Bank, we were able to reset the surface to be 30 thousandths of an inch. In 1983, Algonquin reset their dish to be 33 thou of an inch, which gave them sort of 15% efficiency at 10 millimeters. Now you show them side by side. The Green Bank dish is much taller to its declination axis compared to the elevation axis to the Algonquin. It's like 30 feet higher. Its moving weight was 2,500 tons compared to the Algonquin 9,000 tons. Green Bank is a very rigid structure, which is why their RMS was quite a bit better. So if we do a figure of merit, the diameter squared divided by the wavelength divided by the cost, and look at our telescopes, Parkes was like 227. Green Bank was 90. Algonquin was up at 253. So that all looks pretty good until you look at Effelsberg. Their 100 meters and $8 million cost gave it a figure of merit of 312. first light occurred at Algonquin at May of 1966. There you can see them manhandling the receiver. There they are getting ready to lift it up. There's the cherry picker in the background. This is George Evans, one of the receiver group engineer. The guy in the white coat is Dave Fort. He was a summer student at the time. So here they are raising the receiver up to the focus. And I like this picture. It shows the receiver up here, so they have to tip it up to the zenith and then drop it inside the aerial cabin. But meanwhile, you have the cherry picker here, and this lone figure gives you sort of the scale of the telescope. And here they are installing the receiver. So they're driving around in zenith. You have all these people looking on. Joe Fletcher there is driving the telescope. There's a bunch of people here. Here's Norm Broughton driving it off to the first source. Here's everybody waiting to see a wiggle on the chart recorder. That looks like Ernie Seacrest at the far right. And that's definitely Alan Yen saying, could be, maybe. We do have a log. Ken Eyre, who was the AEI project lead, he was kind of bringing the servo system up on the telescope. And so he wrote, a radio telescope is born, observations on two sources. Let's talk a little bit about how the telescope worked. It could operate in either prime focus or Gregorian mode. So here are our beams coming in. They would get focused at the prime focus. You could stick a receiver through and get your signal that way. Bit of a problem here is that there's 5 feet of waveguide between the feed and the receiver. That's always going to be a problem in Gregorian mode because that adds, when you had a 200-degree receiver, that only added 20. But if you had a 20-degree receiver and you add 20, it impacts your sensitivity. If you remove the receiver, then the beams just go on and bounce down into the Gregorian focus. There's where you put your receiver. So what kind of feed do you need? Well, if you're just operating at 2.8 centimeters, you have this little small feed. If you're at 4.6, you need a feed like that. If you're at 9.4 centimeters, you need a much bigger feed. And so these feeds range from 8 feet to 20 feet in length. As it turns out, they didn't actually use 3 feeds. They used the 2.8 feed, which you then just stacked on removable extensions to change to your different frequencies. So here, this picture that I took way back in 1978 kind of shows how it all worked. Up at the prime focus, you could see the 2.8 centimeter with a big long feed tube sticking through the subreflector. Down in the center there in the vertex, you can see the 4.6 centimeter feed with its scattering cone. And away down here, sitting on the ground, is the extension used for the 9.4 centimeter feed. So it was essentially designed in the early days for only 3 frequencies, particularly if you're using the hub and the vertex to observing. When it was designed, it was assumed that Gregorian focus would be the workhorse mode of the telescope. The gain in the Gregorian mode should be greater than that in the prime focus. The system temperature should be less because any spillover falls on the sky rather than on warm ground. One unfortunate thing about the design was it was designed before sort of beam switching became a way of doing astronomy, and so you couldn't beam switch. You could switch against a load, which is what they had to do, but you couldn't beam switch when you had a receiver in the Gregorian mode. Unfortunately, the Gregorian mode turned out to be a bit of a disappointment. It was unsatisfactory for line work because there was a large 8 megahertz ripple component in the spectrometer baseline. Unsatisfactory for polarization work because of the presence of spurious signals. And unsatisfactory for continuum work at high frequencies because you couldn't beam switch. And people like Lauren Doherty and Bill Laverne spent a lot of time trying to figure out why it never lived up to its original promise, but I don't think they really ever solved what the fundamental problem was. And as it turned out, the Gregorian was more or less relegated to a secondary observations with sort of like a standby receiver. I like this picture. It shows when they were investigating the 8 megahertz ripple that was seeing in the prime focus receivers, which although it had a ripple. It was nowhere near as bad as what was seen in the Gregorian mode. And so they covered over the subreflector with absorber. But what's interesting about this picture, it shows the safety rules of bygone days. Here are two guys standing up in that cherry picker, 100 feet off the ground, and none of them are wearing safety belts. So, a little tangent here, the tale of the mirrored window. Any of you who've been to ARO will notice that the front of the control building here has got this beautifully reflective surface, and you stand on the inside looking out, you see the telescope nicely. If you stand on the outside looking in, you see this beautiful reflection. And so you think, well, somebody was really thinking ahead to make this such a photogenic building. Well, we have to go to the beach. So this is the beach at Lake Travers. It was in the south end. It was very close to the staff house. It was a very nice beach. But you notice there are no beach umbrellas. If you wanted a beach umbrella, you had to go into the control room at 150 foot, and there you see this beautiful beach umbrella. And it wasn't for, in the static atmosphere for the operator. It was because the telescope, the control building faced south. So the sun would just come streaming in, and it was so bright you couldn't see the displays on the control desk. And so here's a picture of Vic Hughes and two graduate students from Queens. I have no idea who. And John Zell is the telescope operator. But there's that beautiful beach umbrella. And so eventually, Bob Dustin would coat the windows with a nice reflective film that cut down the amount of sun coming in. So that cool reflection from the outside was just to get rid of the beach umbrella. So here is the bridge of the HMCS Algonquin. I still think it is one of the best looking and most functionally well-designed control desks of any of the 1960 era telescopes. Notice that the desk is sitting in the middle of the control room, which made it kind of difficult when it came to be adding additional racks for receiver equipment. So they will address that problem. Here's the control room, and in 1965 it looked like this, with the desk in front of the window. There was this huge lab space here, which would become the LBI correlator room in the 1967-68. There's a project office here for Mike Jeffrey and Ken Eyre. Some offices here. Joe Fletcher was in office number 2. Carl Epp was sort of the senior technician up there. But there was a stairway right here. And when Joe told me this, I said, I don't believe that. There's never a stairway there. So he had a picture. He took this picture when he was having his job interview, and there's that stairway right in front of that building, that wall. So by 1968 and through 1987, the things were modified a bit. The desk had been turned around. There's now plenty of room for racks for receivers and stuff here. The stairs had been moved into a little alcove here. This became the room for the computer, the cell 840A. This back room became the correlator room from 68 through 1972. Astronomers had their room here. Joe put his hydrogen maser in there, and then this is where the filter bank spectrometer went. Just to show a picture of how much equipment is needed for LBI, this is the LBI Record and Playback Center from 1968 through 72. There's an awful lot of equipment in there. I'm going to talk about the receivers, but before I do, I just want to talk about a modern receiver so we can sort of put things into perspective. So this is a upgraded EVLA C-band receiver that I worked on shortly before I retired at NRAO. It's a fairly simple layout. You sort of have a feed and a polarizer, and that you then feed your left and right polarization channels into a couple of LNAs, and then it comes out of the doer. You have a noise diode for calibrating the system. For this receiver, we had a receiver temperature less than 10 degrees across 4 to 8 gigahertz. And on the telescope, you'd have a system temperature of less than 25 degrees. So these receivers, very broadband, very sensitive, but very simple. Now let's look at a receiver from 1976 for the ARO. This is a 4.6 centimeter receiver. There's the heart of the receiver where the cool single channel pair amp was. There's a picture of the receiver. It looks somewhat more complicated than our EVLA receiver. And what the heck is all this stuff for? There's just oodles of stuff sitting in front of the receiver. There's like 4 waveguide switches and coax switches, and so I was not a receiver engineer when I worked at ARO. I was the back end guy, and so it wasn't until recently that I started studying why the receivers were this complex. So if you were observing in total power mode, you'd have your main beam coming in, feeding through this waveguide switch and directly into the paramp. That's your most sensitive way of working, but these were parametric amplifiers, and parametric amplifiers aren't particularly stable, and so you'd really like Dicke switch. You had a noise diode that allowed you to calibrate your receiver, and you'd end up with a system temperature of about 70 degrees. But you really wanted a Dicke switch so that you didn't have gain stability problems. So now your main beam gets fed into this Dicke switch. The other side of the Dicke switch looked at a reference beam, and so now your Dicke switch flips back and forth between these and feeds it off into the paramp. You would end up with sort of a receiver temperature of about 100 degrees. So you've added about 30 degrees because of that warm Dicke switch. But normally you'd really like to beam switch. You'd like to beam switch, but you can't always beam switch because you've got an extended source, and so your reference beam is also looking at the source. So you end up having to use a reference load. And so in that case, there's your main beam going to the Dicke switch, and now your alternate path is coming from a terminated load inside the cryostat, which was typically 20 degrees, but by the time it got to the Dicke switch, it was like a 40-degree load. And the problem with that is that your reference load is much hotter than your main beam. And so it's way much hotter. And that means if you have gain instabilities, you can end up with artifacts that you don't want. So what you have to do is add noise to your signal, which sounds crazy, but if you get those 2 signals roughly the same, then gain instabilities don't affect your data. And so to do that, you had a noise diode that adds noise to your main beam. In degrading your system temperature, there is actually advantages to doing that, but you end up with a system temperature that could be like 140 degrees. So now we've essentially turned a 50-degree receiver into 140. In the early days of ARO receivers, they were all pretty well tunnel diode amplifiers, being the device of choice in the late 60s. They provided wide bandwidth and relatively low noise, and were fairly cheap. Some receivers used mixer receivers. There were no amplifiers until after the mixer, so that made them kind of insensitive. Parametric amplifiers back in those days were mostly warm and fairly narrow band and had stability issues. In the early days, continuum were the only observations that you tended to make at ARO. There's little call for heterodyne receivers because they didn't have a spectrometer. So essentially what they used were what was called tuned radio frequency receivers. Essentially a fixed tune amplifier followed directly by an RF detector. So what comes out of the receiver is the detected power, not an RF or an IF signal that you can then mix down and feed into a spectrometer. So they're fairly simple receivers. And so here's what some of them look like. Here's the 9.4 centimeter TDA. It was 900 degrees system temperature. The 2.8 centimeter TDA was 1100 degrees. There was a heterodyne receiver at K-band, 1.3 centimeters, but at 3,000 degree system temperature. And of course the receiver used for LBI, 408 megahertz, was about 200 degrees. These receivers mostly look like they have been designed to put on the 10-meter telescope that John talked about earlier. Receivers that were specifically designed for 150 foot would look more like this. Here's the 4.6 paramp. It was a room temperature degenerate paramp, which meant it was really unstable. And it had a 400 degree system temperature. There was another warm paramp for 2.2 centimeters. It was like 300 degrees. By the early 1970s, you could now buy paramps from the Airborne Instruments Lab, AIL. These were non-degenerate paramps, which were much more stable than the degenerate paramps, and they could be cooled, so that improved your sensitivity. Because they now had a spectrometer at ARO, they needed heterodyne receivers, so that meant all the TRF receivers were sort of thrown away and replaced. Each of these receivers had an internal reference load inside the doer, so that you wouldn't have to add quite so much power to the main beam when you're doing a noise power equalization. So now they look like this. They're now in sort of this rectangular box. The S-band had a non-degenerate paramp, but it was at room temperature, and it had a system temperature of 225 degrees. 4.8 cool paramp was like 50 degrees. The 2.8 paramp was 120 degrees, and the 1.4 centimeter paramp was 300 degrees, but this receiver never really worked all that well. It was very unreliable. So quick diversion to the spectrometer. The first spectrometer at ARO was actually borrowed from the University of Harvard. It was the 21-channel filter spectrometer. That spectrometer had moved around. It spent some time at the 140-foot at Green Bank, and then it went to the Harvard Agassiz station in 1968, and somehow ended up at ARO in 1969. This spectrometer, ARO would eventually get its own spectrometer designed by the receiver group. We think that this is a picture of the 121 channel, but we're not sure, and we're looking for some of the experts here. It's not? Is it? Yeah, but it's on wheels. There was nothing else in ARO was on wheels. Why is it on wheels?
Why is it on wheels? Because Hammond made wheels
Okay, well then this is not the Agassiz, the Harvard spectrometer. But we can talk about the ARO filter bank spectrometer. It was designed by Bill McLeish. He was the head of the receiver group, and he kept copious notes. And so here he is in April of 30th, 1971. Spectrometer, the rack is finished, except to paint. Oh Lord, how long shall thy people wait? And June 4th, he writes, spectrometer, last minute touch-up after the great fall in the shop. Everything goes to ARO on Tuesday. And it went to ARO in June. The initial system was, in rack A, consisted of 100 channels of 100 kilohertz resolution bandwidth. That would be upgraded in 1972 with an additional 100 channels of 10 kilohertz bandwidth. And eventually rack B would be installed to add 100 channels each of 30, 300, and 900 kilohertz resolution. So it was quite a flexible spectrometer system. And here's the picture of the rack A. It was built kind of like one of those Russian eggs that come off in layers. You'd open the front door, and then there was another door you could open to dig into deeper. You open up the back door, and then there was another door you could open. It was really ingeniously mechanical design, and it operated pretty good electrically too. So here's the control rack that was out in the control room. Looked kind of simple. By 1977, it had acquired the name the Jolly Green Giant because it was green, but it had all these pretty different color displays on it that people enjoyed poking and watching the lights come on. Now, so it looked like the receiver group was moving along. They had built a bunch of receivers. And then in 1965, HIA was created. And so a lot of the astronomy sections at the Radio and Electrical Engineering Division were split off and moved to 100 Sussex Drive. And so just as the receiver development effort had reached its stride, this decision would essentially destroy the receiver group. Only one engineer in the group moved. That was Roger Richards. Many of the techs involved in the support of ARO made the move, like Joe Fletcher here. But after 10 years of building up the receiver group, all of its knowledge was lost, and a whole new receiver group had to be hired. So here's an ad that appears in the 24th April 1975 Montreal Gazette, looking for 5 scientists and engineers with different skills. And so from that, we got Bill Blower, Ken Tapping, and C.J. Wu. So the digital guy, well, they had to wait until 1979 when I saw an advertisement and applied. So what about the 5th guy? It says 5 scientists and engineers. Well, they never hired 5 engineers. I think we were lucky when Roger Richards retired that we were able to fill his position with Doug Wade, so at least we were holding our own. So while the new receiver group was sort of being rebuilt, ARO lived on its 4 older receivers, the paramps plus the filter bank spectrometer. Within a few years, the receiver group completed a number of projects. There was a 9-centimeter paramp cryogenic receiver. That was Ken Tapping's job. Modifications to the 1.4-centimeter paramp to see if we could improve its stability. 2 major projects were begun, the 1.4-centimeter maser receiver and the digital autocorrelation spectrometer. Bunch of smaller but important jobs, the new modular back-end signal processing rack, that was Ken Tapping's. A couple of holography receivers. There were things, computerized receiver and control monitoring systems, and then as resurfacing looked like it was on our horizon, work started on a 7-millimeter and a 3-millimeter cooled mixer receivers. So there's an awful lot of work there for essentially a receiver group of 5 engineers and 5 techs who not only had to design and build the stuff, but repair the stuff that was breaking. So a lot of these projects never did come on time. 84, so this is the suite of receivers. The 1.4-centimeter maser was probably the most important one. I only have one picture of this receiver. So that's it. That's all I can show you for the K-band maser. So let's talk about upgraded telescopes. Jodrell Bank was designed to work at 40 centimeters. They eventually got it to work at 6 centimeters after resurfacing. That's a ×6 improvement. Parkes was a 10-centimeter telescope. They got it to work at 1.3 centimeters and a portion of it at 4 millimeters. That's like a ×25 improvement. Green Bank, the 300-foot, was a 17-centimeter telescope. They got it to work at 6 centimeters. That's ×3. Arecibo was 50 centimeters. They got it to work at 3 centimeters. That's ×16 improvement. Haystack was a 3-centimeter receiver that they got to work at 2 millimeters recently, so that's ×15. Algonquin was a 2-centimeter telescope. We wanted it to work at 2.6 millimeters and hopefully even 1.3, so that's ×16. So, compare that to Parkes. That's not an unrealistic proposal. So, telescope was commissioned in 1944. It became apparent that the high frequency limit was not the structure, but it was the accuracy of the panels. So proposals for a new surface soon appeared. In fact, there were 22 separate occasions between 74 and 85 where the Associate Committee on Astronomy and the Canadian Astronomical Society recommended resurfacing. And in June of 1983, Treasury Board gave approval for a feasibility study for upgrading the telescope. In 1985, August, Freeman Fox and Partners released their design study. In December of 1985, Treasury Board approved $8 million for the resurfacing project. And that same month, the contracts were released with a call for bids. So here's the bid documents. This shows what it had been designed as in '62 and what it would have looked like had it been resurfaced. You can sort of see that there's a new surface. The outer mesh has been removed. The Gregorian system is gone. It now has a Cassegrain optics with a new subreflector and a Cass hut. This drawing is a little more detailed. So the primary goal was to work at 2.6 millimeters. That's the CO1 line at 115 gigahertz. And if we could sort out the gravity compensation, we could get it to work at the CO2 to 1 line at 230 gigahertz. The initial surface error was expected to be 160 microns. That's an aperture efficiency at 2.6 millimeters of 22%. With 3,000 motorized adjusters, which had been designed to compensate for the gravity distortion, an RMS of 100 microns was expected. That's a 45% aperture efficiency at 2.6 millimeters and at 1.3 millimeters good weather. And strangely, there is good weather up there because it's so bloody cold. There's no water vapor in the atmosphere. So a 3 millimeter precipitable water vapor would give us 82% transmission through the atmosphere. For pointing, the master equatorial would be upgraded, and it was expected to achieve pointing errors of less than 2 arc seconds. So here's one of these plots that, you compare it to contemporary telescopes. So there's the 2.6 wavelength line and the 1.3 millimeter line. Yeah, and so here's the Algonquin dish. You can sort of compare that with Noviama, so it's quite comparable. The 30-meter IRAM was a precision telescope designed from scratch, and we were quite competitive. Here's the JCMT, which was then called the UK Netherlands telescope. We were actually more gain at 230 gigahertz. Here's what the optics would look like. The low-frequency receivers would be down in the old Vertex hub. You could have two of those. Up in the Cassegrain cabin, you would now have your 4 millimeter wave receivers. So that's 6 receivers in total on standby, right? And if you wanted to work at lower frequencies, which I'm sure the VLBI guys would have wanted, you'd have to remove the subreflector and then put the receiver at the prime focus. So if you look down in the Vertex cabin, there's where the Q-band and the K-band receivers would go. Here's the mirror that is looking up at the subreflector. It bends the beam off to these mirrors here, which allow you to select the Q or K-band. Up in the Cass hut, where the 4 millimeter receivers sit, the beam comes down off this mirror and heads off to whatever receiver you want. You have a couple of mirrors to select. You could also look at a reference beam, so you could beam switch. Plus, you could also put in a hot-cold load for calibrating the receiver. Receivers that were planned was, the first priority was an 8 millimeter receiver to do holography so that you could set the dish. And as I mentioned before, there was work had already started on the 7 millimeter and the 3 millimeter receivers. And there were plans later on to get involved in SIS receivers for 115 gigahertz. Spectrometers, they'd have the autocorrelator and a new acousto-optic spectrometer that we had bought from Elson Electronics in Finland. So the idea was that when resurfacing was done, all the receivers and spectrometers were in place to start producing science as soon as the telescope was evaluated. How much would it cost? Well, the direct resurfacing costs were $7.7 million. So the main contract and auxiliary contracts is up at the top here. There are a bunch of subcontracts for de-icing control, heated panels, motorized adjusters, air circulation to keep the telescope at a constant temperature. Money was also planned for completing the receivers, a local oscillator that was to be built out here at the DRAO, improvements to the MEU, a brand new VLBI recording terminal. That's essentially a VLBA terminal. So total would just under $10 million. But it was not to be. Here's the chronicle of the demise of ARO. In March, Don Morton becomes director. May 2nd, NRC places resurfacing project on hold because of upcoming budget problems. October 9th, the announcement by the Mulrooney government that NRC would be hit with a $26 million cut from its $400 million budget. The NRC management decides that $13 million of that had to come from the laboratories. There were 200 layoffs in total, 20 of which would come from HIA. And so at that point, resurfacing was still on the table, but hanging by a very thin thread. And on October 30th, NRC announced this resurfacing canceled. Activities at ARO would be reduced, and it would be put into mothball in May 31st of the next year. 14 people laid off at ARO. In Ottawa, 5 permanent staff laid off, none of them astronomers, by the way. In the receiver group, 4 of its 8 members were laid off. And so up until May 31st, 1987, the staff that survived worked hard to install a new Google computer and the autocorrelation spectrometer for one last hurrah with the K-band maser during the 46 meters final winter season. So it was a perfect storm for closing ARO. When we had gotten the approval to do the feasibility study, everybody's focus went to making sure the telescope, when resurfacing was finished, would be ready to go. So there was a heck of a lot of work that went on to, pointing evaluation, how well will the telescope point, all kinds of holography measurements were done, design studies for panel heaters and air circulation and a new millimeter wave optic system. So there's a heck of a lot of work that went into making sure the telescope would be ready. But the flip side of that coin was that while all that was going on, the 46 meter was largely unavailable to its user base for a couple of years. And then the Mulrooney's cut came along. Canceling the resurfacing saved 10 million. Closing ARO would save more. So guess what they chose? We had told NRC management that 46 meter was no longer world class and had to be upgraded. And so when the project was canceled, its future was compromised. So in hindsight, that was probably a bad plan, telling them that it wasn't any good unless it was resurfaced. However, the Freeman-Fox design had been delayed because the Technical Advisory Committee were seeking several options to make sure the best option was chosen. Had they not delayed the final contract with Freeman-Fox, then the contract could have been signed before the cuts were announced. Then what would have happened? It was kind of morbid to thought what a HIA would have done with a commitment to a contract. So closing DRAO, for example, would not have saved enough money. So how do you do it? Anyway, what did we spend on the resurfacing project? So here's all of the money that was spent on contracts and on hardware. So you can see $1.3 million. Conservative estimate of the staff members' time spent on resurfaced related projects alone is 1.5 million. So that's like $3 million down the tubes because nothing ever came of it. NRC had made a commitment to keep the telescope in an operational state for 3 years and trying to find somebody to take it over. Meanwhile, Natural Resources Canada and York University used the telescope for VLBI projects. In 1991, ARO was leased, at least was my understanding, was leased to the Institute of Space and Terrestrial Science, a consortium out of York. It was renamed the Algonquin Space Complex. 2006, by then, sites 1, 4, and 5 had been torn down. Until 2006, NRCan would turn the telescope on a couple of times a week and do crustal dynamics until one of the azimuth bearings failed. 2007, it was leased by Thoth Technologies. They replaced the bearing, and now we're using it for telemetry and tracking services, geodetic VLBI, and other types of radio astronomy. So we're going to end up here with a few pictures taken by Drones Toronto. Thoth Technologies had them come up with their drone and take some pictures. And so you can see Petawawa River flowing by here. You can see the fire break around the observatory. There's Site 2 over here. And with drones, you can just keep on flying in closer and closer until you're right up there. Here's a picture from west looking east. There's Lake Travers in the background. Here's a picture east looking west. Essentially, they're out over the lake. And you can see the Petawawa River here. Site 5 is out of the picture here. You can't really see it.
Why is the fire break asymmetric?
Summer students. The one thing that I took out of this picture was, look at all the standing water. Now we know where all those damn mosquitoes and black flies came from. This is what it looked like in 2008. This is what it looked like in 2013. So Thoth has been doing a good job of keeping it painted and hopefully all the rest. So just end up and say the 150 foot was undoubtedly one of the best, most cost-effective centimeter wave telescopes ever built. But because of a perpetually understaffed receiver group, the receivers are really never up to snuff. Based on the success of other telescopes, I think we had high expectations that resurfacing would have succeeded. The optics that had been planned for the upgraded telescope would have been very capable in a flexible observing system. No matter what support resurfacing head within the NRC or its university base, the cancellation was a direct result of cuts imposed by the Mulroney government. So if there's anybody to blame in this sad farce, it's Mulroney government. I think it's the ARO of Canadian astronomy. When NRC walked away, it was the first major national facility to face being mothballed, but through the perseverance of York and NRCan and Thoth, it still remains in operation today, although at a much reduced level. And so here are a few doodles from Brian Andrews from a cartoon back in 1973. Do you want me to do I'm going to do a promo here for Tim and the end of the universe, to the edge of the universe. So this was a film that came out in 1969. There were 7 hours of film footage done by the National Film Board at the construction of ARO, of which only like 10 or 15 minutes shows up in this video. So somewhere there's 7 hours of archival material. But we also have DRAO in here. But more importantly, and here's the footage was really exquisite because they show all kinds of parts of the construction of the telescope in glorious color, which is available nowhere else. But more important are the cast of characters. Many of these are no longer with us. John Galt, Norm Broughton, Alan Yen, Tom Legge, Jack Locke, Bill McLeish. There are a couple who are still with us, in fact, Joe and John. And rumor has it that they will be, for those people who are fans of this documentary, that Joe and John will be signing autographs out in the lobby after this. They're only charging $10 a copy, so it's a real bargain.
Okay, Bob, before you're finished there, I got a couple words to say. Sure. First of all, you can look at the edge of the universe, and you can look for me at both ends of the baseline at once. Okay? That's through modern technology. And the other thing you can note is that the clock is getting loaded onto the wrong railroad. It's an empty box that I had made in the shops, and they just painted it. All right. Guys have nothing to do with ARO or with long baseline interferometer.
Artistic license, apparently.
And we'll be showing that starting at 1 p.m. sharp. So if you've seen it before, you can continue your lunch. If you haven't and you want to check it out back here at 1, we'll just start it up.
Yes, one other thing, on the front table up here are the outtakes of the first BLBI fringes, and the piece of cardboard there are my notes as to what was going on. You'll see the picture of the dish. These are all of my scribbles. Then you'll see the receiver, then you'll see the correlator, then you'll see a table up at its end, and you'll see charts over it. And me with a Polaroid camera taking those slides, so these guys could go to the ERC conference in 3 days.
All right. We'll hear more about that after lunch. So questions or Bob?
I'll start with Jasper.
Sure, Jasper.
I just want to comment on one thing. When you put up your slide of the catastrophe, of the chronology of the catastrophe, you put Don Morton's name right at the top in 1986. I don't think that's fair to associate it with it. I think, speaking to Don after, he was absolutely pretty horrified as to what he had to do.
Yeah, well, we do know that when Don came for his job interview as director, he was wanting to propose that NRC become part of the UK Netherlands telescope. So very early on, he was eager to have Canada join. So it was not his fault that we were closed. Many of us think he could have fought harder.
Yes, Tony.
Yeah, one of the things you didn't mention that made an enormous, this is sort of funny, but one of the things that made an enormous impression on me as a young summer student there was the food.
Yes.
Because this is the only observatory I've ever encountered where they had an on-site chef, dinner with the white tablecloths and everything. And It's all been downhill for me
Yeah.
since then.
Yeah,
You don't like the ARO chef, Tony?
yeah. I'm preparing a second talk, which talks about the 10 other telescopes that were at Algonquin Park. The 46 meter was the 11th. There were 10 other ones there. And Staff House would have been lots of pictures of none of the food, but where you ate and that beautiful view sitting, looking out over the lake.
All right. Other questions, Rob? Yes, Reynolds.
You'll love this. Anyone who worked there is going to find this very funny. I guess in the first 15 years, I think it's going to happen. An article in the Toronto Star appeared, and there was complaints by an environmental group about how the site of the telescopes were turning it into something just like suburban Toronto.
All right. Other question? All right, well, let's thank
Well, I'm going to end up with one thing. Did you know that there is a stamp that commemorates the iconic Karl Jansky telescope in glorious color? And can anybody guess at what country produces this stamp?
One of the African countries that puts
Yes,
out every
that
year.
great mecca of radio astronomy, Rwanda.
All right. Well, let's thank Bob again.